Thank you, and thank you guys for coming to our talk today. We're going to be talking about fastplotlib, which is an open source library for doing general purpose scientific visualization. So Kushal and myself are both PhD students, and we work with a lot of high dimensional large data. And so we're going to show you some cool use cases and also just give you an overview of the library. And so kind of to motivate why we even started developing this library is how important it is to look at your data. So this is just kind of a classic example of, visually what you're seeing is very different, but all of the summary statistics are the same. And so, we work with a lot of ML models or doing a lot of statistics, and looking at your data is really important, and kind of interpreting what you're seeing from your model and aligning that, and also to answer scientific questions. But with that being said, data visualization can be really hard. The rendering needs to be fast. And also, when you're working with a lot of high dimensional data or, large data, it gets really difficult really fast to synchronize your data across different dimensions, and also when your sampling rates are very different. And also to have interactivity between, different parts of your data is really challenging. And a lot of libraries, especially in the Python space, might not allow this very easily or readily. And so that's kind of the problem that we set out to solve when we started building this library. And also, the difference in graphics, 20 years ago versus now, there's been a lot of improvements, and you see that in modern video games. So on the left is a Penguin Racer game from 20 years ago versus, graphics today. And, why don't scientific plots look this good as the video on the right? And so, also harnessing new graphics technology is a big aim for our library. Oh, sorry. Let's see. Okay, yes. So just to give you kind of a brief overview of the stack and kind of what our platform is built on, all the way down to the hardware and how these new technologies kind of come together to create this really expressive library, is, just consider that we have this task where we're just trying to plot this simple RGB image. And at the top of the stack is fastplotlib, and so we've built this library to be really intuitive and easy to use for users, and to be able to create really cool plots very easily. And at this level, it would take only about 4 lines of code to do something like this simple task. You would have a figure, you would have your data, you would add your data to the figure, and then you would show the figure. But as you go down the stack, it gets more and more complex. So right below us is pygfx, which is what we're kind of built on, which is this modern rendering engine. And at this level, it gets to be a little bit more complicated, even to just do this very simple task. And what fastplotlib does is kind of abstract away all of these rendering engine features to make it a little bit easier so that you really get to focus on your data. And things start to get really complicated really, really fast. You need really flexible visualizations that have multiple subplots with versatile tile layouts, or you want to have interactivity, or you want to have labels, and all these things that if you wanted to do that at the rendering engine level, your code would get very big, very fast, and isn't very portable. And so, and if you go down even further below that to the GPU level code, it's hundreds of lines of code just to plot an image. And so our goal with this project was to abstract away all of those really difficult, challenging things so that as the user, you really get to focus on your data, which is, for most people, what they care about. But, pygfx is also really, really cool and is what gives you kind of more of the game-like things or features that you would want to do. So these are just some examples from their library of maybe some more fine-grained things and controllability that you could have in terms of luminosity or meshes or things like that. And the core developers of that are Almar Klein and Karan Van Golen. And they've done a lot of awesome work and helped supporting our library as well. And so we just wanted to highlight some of the features that you get with them as well. And then all the way down to the hardware, what allows these visualizations to be so performant is kind of the innovation of these newer graphics technologies, Vulkan, Metal, and DirectX 12. And the biggest thing is that they leverage modern GPU hardware a lot better than OpenGL, which is what a lot of other open source visualization libraries are built on, and it's kind of slowly being replaced by these newer technologies. But today, we're going to focus at fastplotlib, and that's the library that we develop, and kind of just to put us back into perspective, the goal is to create these really performant visualizations in an easy, intuitive way. And so kind of just a high-level overview of what fastplot is. It's a scientific library. We've taken a lot of inspiration from pygfx and some other popular Python libraries built on top of the pygfx rendering engine. We're still relatively new. We've only been working on this project for around 3 years. And the goal is fast visualization and to minimize the cognitive overhead required for users to use the library. And so the goal is for to think like your data, if you can think in the way of NumPy arrays, then your data can continue, then you can work with your data very easily. And also to have an expressive and elegant API, and we're going to get into that as we walk through some examples in a few minutes. And the core developers are Kushal and myself, and we also have some other major developers at other institutions and universities that we've been closely collaborating with as this project has continued to develop. Oh, sorry. Hopefully you guys could hear me okay. Okay, so what can you do with fastplotlib? It's GPU accelerated visualization, and honestly, like having just a modern integrated GPU in your laptop is sufficient for a lot of use cases. So all of the examples that we're going to show today, Kushal and I made like on our own laptops with just integrated GPUs or well, we might have dedicated GPUs, but anything that's kind of standard is sufficient, and it's great for rapid prototyping and doing algorithm design. And so we're going to do a lot of time series exploration and show some cool neuroscience examples. But Kushal has also done a lot of work doing like matrix decomposition. And basically, if you were in the ML space evaluating and designing your algorithms and looking at the outputs and kind of doing quality control checks, it's really easy to do that with fastplotlib as well. And also, working with really large-scale data and, in use cases where you need fast rendering. And I've also done a lot of work with, real-time acquisitions where you're trying to pull data very efficiently off of, microscopes or probes for neuroscience. And we're going to show some data today for that as well. Where can you use fastplotlib? So the great thing is that, we've designed this code base so that you can basically write your code anywhere or write it once and run it anywhere. So in Qt, in GLFW, or in Jupyter Lab using Render Canvas, which is also developed by the folks that make pygfx. And what allows you is that you can have your data on a remote or cloud infrastructure and then just stream the visualization to your local desktop. So there's no need to have like these really, really large data sets locally. And also it allows you to kind of like maybe be in a Jupyter notebook and be prototyping and then ship it as a full application if you wanted to. And what allows that is having integration with mGUI. And so these are just some example here of using mGUI and also how kind of you can use this in different environments. And so kind of just an overview of the API. So you're going to have a figure, and your figure can have a single subplot or multiple subplots. And once you define your figure, you add graphics for your data. So that could be an image or an image volume, lines, scatters, meshes, all sorts of things. And then you can define interactivity between these subplots or these graphics. And also something that we've been working on more recently is an indie array widget. And so basically, a lot of times you end up with multimodal data that is sampled at different rates or has different dimensionality, and you want to be able to easily interact with those things and sync and slide through different dimensions. And so we've been working really hard on developing this array widget that you basically are able to pass in multiple in-dimensional arrays and then automatically generate sliders for different dimensions to be able to easily slide through them. And that is helpful for synchronizing different data and also like working with really high dimensional data as well. And so now I'm going to turn it over to Kushal, and he is going to walk through some examples and show you guys some cool use cases just to get a sense of stuff that you're able to do with fastplotlib.
All right, so Caitlin gave you an overview of fastplotlib, and I'd like to show you a few example use cases of how we've actually been using this in our own work in collaboration with a bunch of neuroscientists. So I'll show you a lot of examples of how we're using fastplotlib to explore ML models, and although like they're they'll be extensively used to explore neuroscience datasets in these examples, but fastplotlib is a general purpose library, and we've tried to make it useful for various applications in various scientific disciplines and engineering. All right, so let's start with something simple. So let's say we have a point tracking model where we're just looking at the results of some reference points, key points that are being tracked in a video over time. There are a lot of networks that people have been developing over like the past decade in order to do this very well. And fastplotlib lets you visualize videos and things in sync with videos, such as your tracking points or your trajectories very easily. So you can use like this ND widget to look at your video, and then you can also simultaneously add trajectories on it and very easily change what the colors represent, such as velocity or acceleration, or they could be other scientifically relevant features. Here's an example from some data that Caitlin actually works with, where what you're looking at is neural activity that's recorded from a probe that's inserted into the brain. And you're looking at basically the voltage that's been recorded at a couple hundred different sites. And some of these yellow dips you can see here are regions where it's crossed the threshold. And then on the right, you're seeing some lightly processed data. So the kind of like the key takeaway from this here is that all this data is acquired at 30 kilohertz. And it's being streamed by this backend system that's then being fed to the visualization with a latency of like 5 milliseconds from when the data was first acquired. So it's pretty much as fast as you can get. Okay. And here's another example. So fastplotlib is not just for building basic visualizations, but you can also use it if you use MGUI. You can use it to build entire applications that maybe you might want to like ship to end users in a science or engineering setting. So the thing about this is that you can prototype these visualizations in conjunction with, let's say, your model development or your algorithm development in a notebook. And then you can ship the same application as like a Qt app or a GLFW app. Or even like a Vulkan application if you want to keep it in Jupyter without changing very much in your code. So here's an example of some actual model exploration. So this is what's called a QLVM model. It is similar to a variational autoencoder, but unlike a variational autoencoder where you can really only go down to 32 dimensions in your latent space before things start to break down, this QLVM that's being developed by a few people that we collaborate with, they've developed it so that you can go straight down to a two-dimensional latent representation. And fastplotlib is useful for exploring these models because you can very easily just explore your latent space and get an understanding of what your latent space really represents in a way that you can't get with static visualizations. And I'm going to show you some like a real use case of where this QLVM model is being used in conjunction with some real data. So first I'll give you some background on this data set. So this is also some work from a collaborator, and they're working on these animals called Mongolian gerbils. They're kind of like prairie dogs, but they live in Mongolia. And they live in these families in burrows. And similar to prairie dogs, they have these vocalizations for very specific things. Like, if they see a certain predator, they may have a specific vocalization for that, and they communicate with other members of their family using specific vocalizations. And this is all something that these people are trying to study. And what they have is they have like these simulated burrows, like these large environments. This is actually just showing you a portion of like the area that they live in. But they have like this large like simulated burrow system that they live in. And what they do is at the same time, they're also recording audio from the system. And that's what you're seeing on the top is a spectrogram. What's being shown is, you can explore these data sets very quickly to try and find things that are interesting. And, what's kind of being highlighted over here with some of these lines is like the start and stop times for some of these vocalizations that these animals are performing. And then what they're doing is they're passing all of these like interesting vocalization snippets from the spectrograms into a QLVM model in order to try and get a latent representation of all of these different vocalizations that they produce in a continuous space. And fastplotlib makes it very easy for you to explore this latent space, and you can move around in this 2D, or there's also a 3D form of this. You can move around in this latent space and see what do the spectrograms look like in each position of this latent space. And the other thing we're working on is actually integrating this directly with the streaming visualization that I showed you before, so that you can you can look at like what your animals are doing, what is their vocalization, at the same time where is that sitting in latent space. So here's another example of how you can explore models with some real data. So this is actually some data that Caitlin works with, where video is acquired in conjunction with neural activity. So like what you are seeing here on the top is an animal that is performing this task where it has to reach out and grab a food pellet with its hand. So that's a food pellet, and it has to reach out and grab it. And what you're seeing over here on the bottom left is a time series of neural activity of like what is the mouse kind of like thinking while it's putting its arm out and reaching out to grab this food pellet. And what you're seeing down here on the bottom right is a dynamical system model that's trying to create a low-dimensional latent representation of the neural activity. And the cool thing that fastplotlib lets you do is it lets you look at like these different these multiple modalities of data, all in sync, and it lets you perform an understanding of like how is the brain potentially decoding this kind of behavior, and you can just look at your data and try and pick out and see if there's something that your model or your stats is missing. And that kind of leads into into how fastplotlib can help you develop human-in-the-loop ML systems. So this is a bit of a more complicated example. And what is actually happening here is there's some imaging data that is acquired from the brain. That's what you're seeing on the top here. And what you're seeing here on the top left is just raw data that is that's being streamed in from the brain. And then what you're seeing on the middle here is this data after it's been passed through a denoising model. And this is kind of like a mini application where you can change your model parameters for your denoising, and very quickly see how your denoising performance changes. So having these having interactive systems like this instead of just static systems lets you interact with these models, change your parameters, and very quickly see what your results would look like. And kind of where fastplotlib comes in here is that it lets you look through your very large data sets, and you can have multiple panels like this. So like for example, these videos could be hundreds of gigabytes large, and you often have multiple versions of those, and you can basically just look at everything together at once and not be hindered by rendering performance. And here's a kind of larger example of that. So what you're looking at here is not just data that's been passed through some image processing models, but at the same time, you're also looking at like what is the animal doing at that time period. And you have some data that was acquired from various behavioral parameters while all of this data was being acquired. So like what you're seeing over here, I think is like pupil diameter. So, basically they are, they're imaging neural activity in the brain. And at the same time, they are segmenting this out into specific neurons. And then you have a time series representation of like what those, the neural activity of those neurons over time. And then, you're also looking at the behavior of the animal, and you are, inspecting this behavior data to see, does it make sense? Has the model captured these things correctly? You can perform quality assessment, and like in this specific case, actually, it might be hard to see, but a lot of these, like spiky-like things are actually not real, and you can kind of notice that by, if you actually look into your data, you can see that like the pupil tracking is actually very, very noisy. So, this this helps you perform quality control in a way that you can't easily do with static visualizations. And I'll hand it back to Caitlin.
Okay, yes. So we showed a lot of examples, and Kushal and I both primarily collaborate with neuroscientists, so a lot of the data that we showed is neural data. But the really big takeaways at a high level are that, lots of times you have really high dimensional, large scale data, and static visualizations are not sufficient in order to really see what your model output is, and kind of if it's making sense, and also how can you interactively look at both things at the same time, and that's kind of what fastplotlib allows you to do. And we just wanted to show some cool examples of some interactive things that we've done and some current data that we're both working with. But another big thing is that we do have in our repository a lot of examples of showing just the basic things and kind of like how to get started, and we're always adding examples to this all the time. And so, if I just click on this, perhaps I will, so I can see it as well. But basically, we have this examples gallery, and it has a ton of examples, and so like from very basic images all the way to like interactive visualizations as well, and we're constantly adding to these, but this is also a great place to get started and learn a bit more about the library and how you can build up some of these more complicated visualizations for your data. And so, let's see. Okay, yes, and so I can, sorry, if I just pin my microphone again. Sorry, hopefully you can still hear me. But it's really easy once you install the library to just like copy and paste code. So you can open like an IPython terminal and copy and paste, and then run, and then launch the visualization, and then you can kind of see some of the interactivity and things that you can do. So this is just like the same simple image that I showed before, but we also have some more other examples as well that are a bit more complicated, so like some volume data as well that we didn't show much of. But like I said, it's very easy to just kind of copy and paste these examples, and you can kind of move around in them, and you can very easily change features. And so this is something that is available and very easy to use in the library as well. And so basically just say that we're always trying to add more examples and help people with their use cases. And we're always very happy to help you with your visualizations depending on what type of data that you work with. We showed a lot of neuroscience data, but we would love to work more with like astronomy data or other scientific data sets that are relevant. And so just kind of some future directions for the project or ways that we're looking to kind of expand the project to make it more performant, especially maybe on the hardware side, is to add a WGSL JPEG encoder to make the rendering faster so the visualizations become even more performant. And then also combining these visualizations directly with maybe like computations that you're doing on the GPU. And so integration with TinyGrad or like some type of like PyTorch API, so then you really do get seamless integration with your ML models. And so like I said, we would love to help you visualize your data. And so we are happy to interact with you on the GitHub repository, but also by email. And Kushal also, he's based out of New York City, and he runs a visualization group that meets about every 6 weeks. And so feel free to talk to him about that as well. And we just want to say thank you for coming to our talk. And we're going to be around this afternoon and this evening, and we're very happy to chat. And we're also open to collaborations in academia or in industry to help people with visualizing their data. And we also want to say thank you. There are a bunch of institutions that we are collaborating with or are involved with the project and have continued to support us. And so thanks to them as well. And so we're going to be going to the Harvard Gardens for dinner at around 7, or for drinks. Feel free to come by if you'd like to chat. We're also available for the next couple of minutes before our next talk, and we'd be happy to chat or answer any questions at this time. Thank you. Sure.
So I'm familiar with the data shader hollow views ecosystem. Are you able to comment on what are some of the differences between what fastplotlib does compared to data shader and hollow views?
Yes.
Yeah. I've played around with data shader and hollow views. So the use cases are different. Fastplotlib, the idea is you're basically, in order to do large-scale visualization, the idea here is, you just brute force passing through millions of points and have the GPU deal with that. Whereas, with data shader, it is trying to, like, if you have millions of points, I guess it's trying to do like a kernel density estimate in order to get that. And actually, there's one use case that I kind of showed here. So if your kernel for like a kernel density estimate is hard to construct, like it's easy if your data can be estimated by a KDE if a Gaussian kernel makes sense, but sometimes that doesn't always make sense, and it can be hard to determine the right kernel. So perhaps in that kind of use case, like just brute force visualizing everything could be useful. But the other thing is that, like, I guess the bokeh ecosystem is primarily used for building web applications, and it has a JavaScript front end. So whereas like over here, you don't need to know any JavaScript for doing everything basically. Like I guess there's like some customization and some event type things in the in the bokeh space, which is where like you need JavaScript to do things in a customizable way. Whereas here we are, I don't know. I guess like in our world we try and like write as little or no JavaScript as possible. So that's another thing. And I guess the other thing is that I don't know if this is true now, but at least like years ago when I was playing around with bokeh, it uses JSON serialization to transmit data from the Python server to the JavaScript front end, and that can often be a bottleneck if your data is large or if your data cannot be serialized fast in JSON. Whereas what we're using here via render canvas is if your data set is large and you're using remote rendering, then what you're doing is you're rendering on the remote and you are just transmitting like a rasterized JPEG to you. So you bypass having to transmit like real data between your server and client.
But then at the cost of not having client-side interactivity with the data elements. events?
Yeah, so render canvas will then, so you have a canvas on your client side, and any events that any interaction with your canvas is then transmitted to the server.
I think this is really cool. When you showed the example of the streaming visualization, my first thought is, I wonder if this would work if you sort of hooked it up to like a real-time data stream. So I'm curious how well fastplotlib's API works with async. So like if you don't have the batch of data, I'm assuming that the API is sort of assuming that you have a batch of data and that there is some time series feature that allows you to kind of replay the stream. But like, what if it's actually like if the tensors are streaming to the API? Like, would this work with the async package, or is that something that you can sort of see working? Have you tried that?
Yeah, so this data is actually streaming, from like ZMQ, and so I'm like interfacing with the like probe technology and like pulling the data off in real time, and then I just like restructuring it from the buffer into an array that then I like update the visualization with, and so I think it would be a similar situation in the setting that you're talking about. Any other questions?
Oh, and just about async, I do know that, so like WGPU is, it has, okay, don't quote me on this, but I think WGPU's like real implementation is supposed to be all async. And Elmar is trying to work on making basically like the entire stack be able to, run asynchronously. And I mean, I think, yeah, for more details, I'd probably like look at the WGPU and render canvas repo. There's like the async stuff happens more at that level, not at the fastplotlib level.
Thank you.
Does the cross-panel interactivity assume that it's all basically the same data structure and you're just taking different slices of the same data structure? Or could you view it as like a callback where I'm selecting data in this one panel and then I trigger like a Python function that selects data from a completely different data set and then renders that to another panel?
Yeah.
Like a Plotly dash backgrounds and that's sort of how it works there.
Yeah, so basically like when you're defining your interactivity, they are callback functions and you're basically selecting, so like, for example, in one of the plots that Kushal showed, like you have these like ROIs and you're like clicking on an ROI and maybe that would trigger like a different visualization in some other plot. And so you're basically like aligning between different plots or graphics, like the features that you want to change together. And so that becomes a callback function that gets called when that event changes, like I clicked on this, that triggers something else, and then you would have a function that says, okay, when that click happens, what do I want to happen here? Anyone else? Okay, cool. Thank you guys so much for coming to our talk. We really appreciate it. Thank you.